Hi, I'm Igor. Today I'd like to present you my MemoryRanger, which can isolate driver's code and allocated data from illegal access in the kernel mode memory. This topic is of critical importance for all security experts who are dealing with protection of operating systems. A few words about me. I earned my PhD 7 years ago. My area of expertise includes Windows kernel security. I'm a fan of Windows kernel security, rootkit detection, and hypervisors. I carried out security research projects by my own as a hobby. I'm a fan of cross-disciplinary research. You can find my results in my blog here. By the way, I'm fond of traveling and powerlifting as well. I've divided my talk into 3 main parts. Firstly, we'll be looking at the consequences of attacks on kernel memory. After that, I'll give you a brief analysis of Windows built-in security features and research projects which are designed to protect kernel memory. Finally, I'll show you how I solve this problem using my MemoryRanger. Feel free to ask me any questions at the end of the talk. Nowadays, kernel mode drivers share the same memory space with the rest of the OS kernel. All drivers can read and write any part of kernel mode memory without any hardware restrictions. This fact makes the modern operating systems to be prone to rootkit attacks and kernel exploitation. Let's have a look. Malware driver can dump the driver's code and tamper allocated memory, for example, Windows internal structures and allocated data of the third-party drivers. As a result, hackers can escalate privileges, hide their footprints, steal user secrets, or even disrupt industrial processes, which are controlled by drivers nowadays. So, let me demonstrate you some of these attacks. Let's imagine 2 houses with private art collections, Russian house and a British one. In the Russian house we can see the painting of Vasily Kandinsky. You know, he was a great Russian painter. The Banksy's art is in the British house. I hope everyone is familiar with Banksy's painting and the recent scandal with shredding his painting in London. This is the painting. And here is the hacker-attacker who wants to grab all these masterpieces. If these houses are not protected, the both private collections will be stolen. In the kernel mode memory, the situation is absolutely the same. If drivers are not protected, the data can be stolen. Let's see how it can happen. I will load 2 drivers, the Russian driver and the British one, which store their data in the allocated memory pools. After that, the attacker's driver will be loaded to dump the driver's code and steal both Russian and British data buffers. And finally, I will show how the attacker can even escalate process privileges. Let's see how it can happen. I'm launching a Russian console which loads a Russian driver. In the same way, I'm loading the British driver. Finally, the hacker-attacker is launching its driver to access kernel memory. Now, the attacker is trying to dump the Russian driver using its loaded address. The attacker is copying this address, and we can see the attacker is successfully reading the first byte, which is M, and the second byte, which is Z. This is typical PA file header. What about the British driver? The attacker has successfully dumped first 2 bytes as well. we can see that the code of both drivers can be stolen. Now, let's move on to the private data, which can be stored in the allocated memory. The Russian driver is allocating data and setting its content as Vasily Kandinsky. Let's check Kandinsky. We copy this address and reading this data, the data has been allocated. The British driver is allocating memory and setting Banksy as its content. Now, let's check Banksy. It's all right. The data has been allocated. Now, the attacker wants to steal this priceless data content. To steal Kandinsky, hackers need to know the corresponding memory address. Let's assume they do know this address because usually hackers do know everything. So, the attacker can read this data. Let's have a look. Yeah, the Kandinsky has been stolen. Okay. And now the attacker is overwriting Kandinsky using, for example, 4 ones. Okay, let's go back to the Russian driver and check the content. We can see the attacker can read this data and overwrite it. We have only 4 ones instead. We can see that the attacker did modify the data. Now, the attacker is entering the British house to steal Banksy's art. He copies this address and we can see that the Banksy has been stolen, and after overwriting, we use 4 twos, and let's check the original collection. The collection has been disappeared. Both data buffers were stolen and modified. Okay, now let's go back to our slides and close the video. Hacker attacker has successfully stolen both private collections. It means that our houses were not protected in a proper way. What was wrong? How can we prevent this attack? How can we defend them? We will see it later. And now, let's go back to demo to see how the attacker can even escalate process privileges. One moment. Now, the attacker is starting the CMD console. After launching it, he's getting its process ID using this string. Here is the PID, he's copying its PID. We can see that CMD has users privileges. And it is not enough, for example, to reconfigure the Windows firewall. Let's have a look. Yes, access is denied, which is expected. Now, the attacker is trying to elevate the CMD privileges. He's using priv command with process ID. Let's go back and check the privileges again. We can see that the privileges have been escalated. Now, the CMD has the highest privileges, and now CMD can reconfigure Windows Firewall service and even can turn it off. Let's have a look. Well, we can see only a small message which confirms that the Windows Firewall is out of service and it cannot be automatically restarted. This is very good news for hackers. But let's wait for PatchGuard reaction, which is designed to prevent illegal memory modifications. We've been waiting for as long as 10 hours. It is quite a long time. And let's have a look what will happen. And we can see that nothing has happened. The OS hasn't been crushed. It means that PatchGuard didn't prevent this invasion. And the OS became infected. So we can see that Windows kernel cannot prevent illegal memory access. The attacker can read the driver's code, steal and change allocated data, and even escalate process privileges without any security reaction, such as a blue screen of death. Let's have a look at the current situation with memory protection projects. Look at this table. Microsoft has developed a number of security features for memory protection. The first one is Device Guard, which provides kernel code integrity by marking executable pages as read-only. So any modifications of the code will crash the system. Not bad. The second one is PatchGuard, which crashes the OS after revealing some changes of internal structures, for example, EPROCESS unlinking. But you've just seen that PatchGuard doesn't protect EPROCESS structures completely. Finally, Windows security does not protect memory allocated by the third-party drivers. Also, many security experts from all around the world are trying to fill this gap. There are several research projects which are designed for memory protection, and you can see that there is no general solution. No general solution which can deal with all these issues at the same time. Today I will propose the solution. I will present you my MemoryRanger, which provides both integrity and confidentiality for drivers and allocated data. Look at this. Nowadays, kernel-mode drivers share the same memory space with the rest of the OS kernel. If we can move these two drivers with their allocations into two separate memory enclosures, we will protect their memory from each other. The thing is that Windows OS doesn't give us such an opportunity. So, luckily for us, hardware virtualization technology provides the mechanism which can be used to implement the idea of memory isolation. I mean extended page tables or EPT feature. Without EPT, guest physical addresses are used to access host physical memory. Here, address H is equal to address G. Using EPT, we get an additional or second level of address translation. When EPT is enabled, guest physical addresses are translated to host physical addresses by traversing a set of EPT paging structures. We can see that now address H is equal to the address E, not to G. Let's have a look at EPT details. EPT structures includes EPT entries which determine the mapping between the guest memory and the host memory. Each EPT entry includes memory access bits and page frame number, or PFN. So this number is linked to the corresponding host physical address. It can be used to prevent access to the protected data. We can redirect the access from the protected data to the fake one by changing PFN value to the address of fake page. Another feature is memory access bits. They indicate whether access attempts are allowed to the page referenced by this number. Any disallowed access attempts will trigger EPT violations, and then controls goes to the hypervisor. So we can trap read, write, and execute access to the page by changing these memory access bits. And the final feature is that we can allocate several EPT paging structures with various memory access configurations. and by switching between them, we can organize drivers' execution in isolated enclaves. We can see that EPT feature seems to be very promising for memory isolation. Let me show you how all these ideas are implemented in my MemoryRanger. I explored the following scenario. The OS kernel and other drivers are loaded into the memory and access their data. We have only 2 legal access attempts, which are marked by green arrows. As the driver A is loaded, it allocates memory and accesses its newly allocated data. All in all, now we have 3 legal access attempts, which are marked by green by horizontal lines. All horizontal lines are legal access. Non-horizontal lines, which are red, are illegal. We have 3 illegal access attempts. Driver A modifies the OS internal structures, for example, to escalate privileges or to do something more. Other drivers read the memory of driver A, for example, to dump this driver in order to reverse engineering purpose. And finally, other drivers try to overwrite its allocated data, for example, to steal something or to attack this data. As you remember that all drivers share the same memory space, all these illegal access attempts are becoming uncontrolled. Now let's roll back and launch MemoryRanger to isolate driver A from the rest of the OS kernel. First of all, my MemoryRanger allocates the default EPT structure. All loaded drivers and Windows kernel are executed inside the default EPT structure. MemoryRanger traps the loading of driver A and allocates a new EPT structure for driver A. This EPT structure is designed specifically for this new driver. MemoryRanger updates all EPT structures in the following way. Only driver A and OS kernel are executed inside this new EPT structure. All other drivers can be executed in this memory because we restrict their access. In the new EPT structure, memory access bits have been cleared to 0 for OS structures to restrict access from driver A. Here, driver A cannot access OS kernel structures. Also, in the default EPT structure, memory access bits for driver A have been cleared as well. So we can see the following picture. Driver A can be executed only in this memory, while other drivers can be executed in the default EPT structure. So, after driver A allocates memory data, my MemoryRanger updates all EPT structures again. As a result, any access from other drivers to the driver A and its allocated memory will be trapped and blocked. All in all access to the OS structures is forbidden for the driver A. It means that driver A can access its memory only in these EPT structures, and this memory cannot be accessed by other drivers because they are executed in another memory, which this data is forbidden. In the same way, MemoryRanger allocates a separate EPT structure for each new driver and updates all other EPT structures. It looks like a separate driver's content in the kernel-mode memory. This is the main idea of this topic. Let's move on to the demonstration. Let's add one more treasure house to our criminal story. Let it be American house full of Jackson Pollock paintings. Now we have 3 houses with 3 private art collections, and the attacker is more motivated. So to protect these houses, we need to build at least a fence. It helps to prevent attackers' access and also isolates 3 houses from each other as well. In the kernel mode, the driver's memory will be isolated in the same way. I will load 3 drivers. We call them Russian, British, and American. All 3 drivers store their data in the allocated memory pools. After that, I will launch a malware driver in order to steal and modify these data buffers, as well as dumping the driver's code. Finally, a malware driver will try to escalate process privileges. Let's have a look what will happen if I launch MemoryRanger before. Oops. Yeah. Just a minute. Yeah. First of all, I'm launching MemoryRanger console application. It loads the driver and activates the hypervisor. Here is in the left corner, we've got a MemoryRanger console application. Then I'm launching 3 drivers, Russian, British at the center, and American on the right corner. Finally, the hack attacker is launching its driver. Its console will be at the center. Now, the attacker wants to dump the Russian driver first. He copies its address, and we can see that now attacker can read nothing. What about the next byte? He has a 0 value as well. So we can see that attacker fails to dump this driver. Now let's read the content using the driver itself. Yeah, now we have M and Z value. We can see that MemoryRanger can protect the content of the Russian driver. Now the attacker is entering the British house. He is going to dump the British driver. He is copying its address and trying to read its content. Let's have a look. So he gets a 0 value again. MemoryRanger is foisting the fake null data to the attacker instead of the real one. Now let's try to access the British driver using the British driver itself. We're reading this data, and now we're reading M and Z bytes. It means that MemoryRanger can prevent unauthorized access attempts and grants the legal access. And now, let's check if the American driver can dump British driver without attackers. Yeah, we're moving to the American driver and tries to dump the British driver. We have 0 value again. MemoryRanger isolates drivers from each other. Any applause? Okay. Thank you. Now let's move on to the private data which can be stored in the allocated memory. For the Russian driver, I'm allocating Vasily Kandinsky. Now let's check the allocation. Vasily Kandinsky. Data has been allocated. For the British driver, I'm allocating Banksy. Now let's check the allocation. And finally, now we're moving to the American driver. I'm allocating the data and setting Jackson Pollock. Now let's check this allocation. Finally, Jackson Pollock. Now the attacker wants to steal all these treasures. Let's see if he does manage that. He's starting with Russian house and Kandinsky art. He's copying its address and tries to read. Let's have a look. Yep, the attacker can read only a null string. Now he is trying to overwrite this data using for once, for example. It's time to check if the Kandinsky has been modified. We read the data again, yeah, and we can see that MemoryRanger is protecting this data. Hackers failed to steal and modify Kandinsky. Now, the attacker is entering the British house to steal Banksy. He's copying its address, and we can see that the attacker can read nothing again. Now he's trying to overwrite this data. Now we go back to the British app and check Banksy collection. Yeah, we can see that MemoryRanger is protecting Banksy as well. And now, finally, let's check if the American driver can steal Banksy collection from the British house without attacker. We're moving to the American driver and tries to read Banksy collection. Yeah, no result. Now he's trying to overwrite this data using American driver. Let's check the collection. We can see that MemoryRanger is isolating drivers allocation from each other as well. So we can change the data only by the driver which allocates this very data before. Let's check it. Let's replace Vasily Kandinsky with Ivan Ivazovsky. He was a genius Russian painter. We double check Vasily Kandinsky and overwriting it, replacing with Ivan Ivazovsky. And let's check the data again. So the allocated buffer has been updated in a legal way. MemoryRanger is protecting even allocated data. Now, let's check a privilege escalation attack. The attack is launching CMD, getting this CMD identification, and checking the privileges. As we expected, CMD has uses privileges and cannot reconfigure Windows firewall, which is expected. Yeah, access is denied. The attack is trying to elevate the CMD privileges. The attack is using priv command with process ID. Let's check the privileges. We can see that CMD has still uses privileges and cannot reconfigure the Windows firewall. It means the attacker is failed. CMD is not able to stop Windows firewall service. The OS is protected. Any applause? Oh, thank you. So you've just seen that this is kernel mode drivers with a small fence. Yeah. You've just seen that MemoryRanger prevents illegal memory access by running drivers into isolated kernel spaces or enclosures. Let's have a look at memory access rules which are provided by MemoryRanger. MemoryRanger protects memory according to the principle of least privilege. Newly loaded drivers can access only their own code. The read and write access to the data is granted only to the drivers which allocate these data buffers. All other memory access attempts are blocked. MemoryRanger protects drivers' code from being dumped. It prevents read and write access to the allocated data. And finally, it prevents a privilege escalation attack. Now, let's move on to the MemoryRanger architecture. This MemoryRanger includes the following three parts: MemoryMon RWX, which is on the left, the central component is DDIMon, and the final is Memory Access Policy. The first two parts were developed by Satoshi Tanda, he's a genius researcher from Japan, during our collaboration. MemoryMon RWX processes the loading and new drivers and and processes as well as all EPT violations, while DDIMon installs the invisible hooks on kernel functions which allocate and deallocate memory. I developed a memory access policy, which is a kind of brain for the first two parts. For each newly loaded process, MemoryRanger adds the following structure to the list. This structure includes process ID and the address of its EPROCESS structure. For each newly loaded driver, MemoryRanger adds the following structure to the list. This structure includes an address of allocated EPT structure, which is allocated specifically for this driver, as well as driver start and end addresses, and a vector to collect memory addresses which will be allocated by this driver. Each time the driver allocates memory data, MemoryRanger adds the following information to the list. This structure includes the data, the address and the size of newly allocated data. Memory access policy manages all these lists and decides to grant memory access or to deny it. All the details about MemoryRanger architecture are in my white paper. To put it in a nutshell, the MemoryRanger dispatcher is here. It processes 3 EPT violations, read, write, and execute, and 1 VM exit. For execute violation, MemoryRanger changes pointer to the appropriate EPT structure, so the kernel-mode code continues its execution into the corresponding EPT structure. It looks like swapping context in user mode application, but in the kernel mode drivers. For read and write violations, MemoryRanger checks whether this access is legal, and for illegal access, the MemoryRanger changes PFN value or page frame number of the protected data to the fake one and allows access to this fake data. And finally, it sets monitor trap flag. As a result, after a driver reads the fake data, the control goes to the hypervisor again, and now MemoryRanger restores PFN value to the protected data and blocks any access to this page. Finally, it resets the monitor trap flag. Here are steps to add a new data to be protected by my MemoryRanger. First of all, you need to create a list of addresses and sizes of memory regions which are needed to be protected and clear access bits to restrict the access. Don't forget to update your list, for example, using callback functions. Then dispatch EPT violations which occur during access your data. To process all violations, you have 3 input parameters: type of access, read or write, address of module which tries to access, and finally the address of data which has been accessed. It looks like IP addresses. We've got source address and destination address, who is trying to access, and what kind of data this module tries to access, and type of access, read or write. You can only monitor the access attempts as well as redirect them. Now, let's move on to the final step, which is the benchmark assessment. I measure the time of legal access from driver to the allocated data in 4 situations: without memory protection, with enabled cache, with disabled cache, and with 2 memory protectors, AllMemPro and MemoryRanger. AllMemPro, or allocated memory protector, is the closest competitor for MemoryRanger, which I developed a year ago as well. AllMemPro uses only 1 EPT structure to prevent illegal access attempts only to the allocated memory. We can see that MemoryRanger is a bit slower than access to the memory with disabled cache, and it 3 times faster than the closest competitor. We're close to the end of our dramatic story. Let me recap very briefly on what I've presented and what you learn. First of all, I've demonstrated that drivers can access kernel mode memory without any security reaction. Then I've presented MemoryRanger, which can prevent unauthorized memory access by running drivers into isolated enclaves. Finally, I'd like to highlight one important thing. I suppose that MemoryRanger seems to prevent the recent side-channel attacks like Spectre and Meltdown, and I think it will be interesting to test this MemoryRanger using these attacks, and if anyone has a prototype of Spectre and Meltdown, please send it. I will test, and we will see the result. And I just like to conclude with old Latin expression. It is on the screen. This is very famous expression. I believe that it is applicable not only for ancient Sparta, but only for kernel mode drivers in newest Windows. Thank you. That's it. And now, yeah. And now we're moving to the most interesting part of today's topic for your questions. Please, raise your hands. We've got just one question.
Hello, thanks for the talk. Is it correct, my understanding correct, that you can only use MemoryRanger on x86 platforms? So it's like architecture specific.
The thing is that MemoryRanger is based on hypervisor facilities, and it works on all platforms which supports VTX technology with EPT, provided by Intel. Not only for Windows, this is, let's open some interesting slide with MemoryRanger architecture here. There are a lot of projects for Unix operating system which focusing on similar tasks, yeah. And for ARM architecture, you know, they've got similar hypervisor facilities, yeah.
So technically it can work on ARM.
It can technically work, I think, in all Intel computers, which has been sold for the last 10 years, yeah. For AMD computers, we've got similar technologies for the last 10 years. And I think for ARM computers as well.
Okay.
Yeah.
You also mentioned there are Unix solutions.
Mm-hmm.
How it would be different on Unix? So for example, like on Linux systems, I know that like Linux likes to pass internal data structures from one piece of code to another. So technically, you can operate on an internal data structure which is not necessarily, it can be allocated by another driver, and you have a legit need to access it.
Yeah. This is very complicated question. The thing is that nowadays MemoryRanger does not provide shared access to one memory for two drivers, but access policies can be adopted, yeah, to improve it. The thing is that now rules are quite simple, yeah. Only driver who allocates memory has full access to this data. All other accesses can't access. But my idea is we can generate a memory access rules on the compile phase when we compile our drivers using Visual Studio. In the development phase, we can generate, because developer always know which memory, because, for example, several drivers usually compiled in the one solution, and now we can prepare appropriate memory access rules. The thing is that for Linux-based solutions, they've got operating system with open code. For example, Linux, Ubuntu, and a lot of, and they got more mechanisms to protect memory. Yeah, in my paper, yeah, I want to, if you, yeah, you can read my paper. There are, I think, about 30 projects which are focused on precisely this topic, how to protect memory, and vast majority is developed for Unix-based systems, not for Windows, just few for Windows.
Thank you.
Thank you. Actually, this is the big problem with memory protection in kernel mode, because the main idea of Microsoft company is that kernel mode drivers do not include malware or don't have vulnerabilities, and we always trust kernel mode. But nowadays we can see a lot of examples of malware which can leverage drivers' facilities. We can a lot of drivers which can include vulnerabilities. Yeah. Attacks, for example, Stuxnet is old-fashioned attack, more than 10, 12 years ago. Yeah. The thing is that I think it will be a good idea to implement the mechanism of process switching between process, like process context in the kernel mode, yeah, especially for Windows, because they've got source code of their kernel, and we can protect these drivers. Oh, we've got one question more. Thank you.
So as far as I know, Hyper-V also uses Intel EPT. So does your software run next to Hyper-V, or is there a problem to use it both on one system?
The thing is that I've tested MemoryRanger without Hyper-V, and this is quite an issue to work these two different solutions which use same technology, virtualization EPT at the same machine. This will be my next steps to check not only with Hyper-V, with another technologies like with antivirus systems. That's it, but maybe Hyper-V will integrate MemoryRanger principles. Yeah.
Thank you.
Oh, we've got one more question.
So it works only on newly loaded drivers?
Yeah, only newly loaded drivers, yep.
So it should be possible to unload the driver and load it again?
You mean that load a driver and then unload?
Yes, if a driver is previously loaded, unload it and load it again in order to be protected.
Yeah, to avoid this protection. Yeah, yeah. The thing is, I haven't tested your scenario, but the current version of MemoryRanger is just proof of concept prototype. It doesn't support unloading drivers and deleting context, EPT structures. Yeah. I assume that drivers will load it in a legal way, like using service control manager, because there are various hackers approaches to load kernel mode code, and continuous way working, just like NVIDIA drivers. Yeah.
So this would be a suggestion. If a driver is already loaded, to, I don't know, find the memory allocations and remap them using a new EPT to protect existing loaded drivers.
Yeah, you mean just patching EPT rules? Yeah.
Yep.
Yeah. Thank you for a question. It's a hack, absolutely. Yeah. Thinking about, yes, you're right. You can now this in the current version, memory access, memory rules. Yeah, they do not protect it from being read and overwritten. Yeah, you can change rules. Yeah, but it can be possible to protect these rules using specific EPT structure for MemoryRanger and these rules. Yeah.
Okay.
Yeah, this is one of the key point. Yeah.
Thanks.
Yeah, you understand everything. Thank you. We've got some minutes. Yeah, 5 minutes. Oh, we've got one more question.
How do you protect your driver when you are booting your machine from another maybe malicious driver that was already installed on your machine, maybe we'll try to disable your driver and avoid this protection and disable these protections.
Nowadays, I do not provide any mechanism to protect my drivers from malware driver. I just consider this scenario to, yeah. But it's possible to implement some ideas, but it's only arm race, yeah. How many techniques do you know? How many techniques I implemented? Yeah. Also, if we got a few minutes, I can show you one more demo. Do we have some more questions? No? No, let's see one more demo. Without sound, but yeah. This video will demonstrate an early version of MemoryRanger. Yeah. And we can see another interesting question, how often we need to swap context between different EPT structures to protect our driver. First, we launch MemoryRanger. Yeah, MemoryRanger has been loaded. Yeah, now we're loaded memory which allocates memory. Copy is address and try. Yeah. Yeah. Here in this list we've got strings which shows the switching between the default EPT and the protected EPT. Here is from the default to the protected, from the protected to the default, and etc. You can see how often we change our EPT pointer between various drivers. In this case, we've got only one protected driver and all others. All other drivers are loaded in the default EPT. Only one driver, which is memory allocated, loaded in the protected. Just, for example, how often? And this is attacker. Attacker is loaded into the default EPT structure. Now attacker wants to dump this driver, and we can see, yep, that MemoryRanger intercepts illegal read access. Yeah. Let's have a look. Yeah, and what about the next address? Yep. And this, yeah, we've got only one read access because we read only 1 byte. Now it's time to check allocation. I allocate just A, B, C, D. Yeah, we demonstrated that the memory has been allocated. Yeah, here is the point. Now we're reading the content of our driver using our driver itself. We've got a minute. Yeah. And to read just 1 byte, we need to got a lot of switching between EPT constants. You know, because we've got scheduler, we've got a lot of file system drivers which need to be executed, and you can see how many. 1, 2, 3, 4 switching to read just 1 byte from our protected driver. Yeah, we'll go just 1 minute and we'll go. Yeah. Now it's time to check allocation. We allocate A, B, C, D without painters. Yeah, you can see how many interceptions, how many switchings is needed to allocate few bytes. Yeah, but anyway, we copy this address and move to the attacker. We double check the data has been allocated. We try to overwrite this data. Yeah. Yeah, this is our data, and the data has been allocated. We got double F at the end. Yeah, we restore and now we try to access this data using another driver. Yep, and the data has been protected. And you can see there are a lot of interceptions, switches between protected driver and not protected. Yeah, this is close to the question about benchmark assessment and how fast MemoryRanger is working. And that's it. Yeah. Yeah. Thank you. Thank you.